Thank you for your kind introduction, Dr. Zhang. It's certainly a privilege to be back at CMA and in SNC, where I have so many dear friends that I have met over the years. It is especially wonderful to be here with my good friend and colleague, Dr. Paul Menzel from Wisconsin, as we talk about a number of things in training that we're doing with some lectures here, but also in the planning for your future satellite system. The talk this morning will deal with, it says polar and geostationary satellite synergy toward optimum utilization and relationship in GEOS. And I imagine in some ways the talk will address that, but it will address a number of issues, a number of opportunities, and it will talk to some things that I think are vital for us as we move forward in our space-based observing system. So I think it's important that we realize several things as we look forward. We're in a science of change, but when we look forward, there's always the need to look back. And you will see why in a few minutes. For basic resolution, we'll talk about systems coming up in the next decade, some synergy examples and so forth, exploitation and how do we move forward, some challenging thoughts in that area. What I have here is a chart that shows the launch year, and these are Earth observing satellite missions, so they're not the ones that go into deep outer space, but they're the ones mainly to look at the Earth. And you will notice that we start back with a few satellites early in the period up until the 1990s. We have research satellites, operational satellites, land observing satellites. Then as we move more and more forward into the future, we notice that we are getting more and more satellites, and some of these have a number of specific missions, satellites from China, satellites from Europe, the Russian Federation, from Brazil, from the United States. Great numbers of satellites, and right now this period we're in has often been called the golden age of satellite observing of the environment. And we need to make sure that golden age returns what it should and remains a golden age for those that follow. This is just a continuation of some of those missions, and you'll notice as we're getting out in here into the later years, and we have our FY3 missions, FY4, and others that will come. So we're really in an area of exploitation and utilization. This environmental observing of the Earth started back in a serious nature in 1960 with the launch of TIROS-1. There you see it going off of the launch pad, and the first image taken by that satellite over Nova Scotia. These were uncalibrated Vidicon images. Over 45 years later, we've moved into a totally different age than that initial era. Satellites are providing high-resolution digital data from a number of spectral bands, and we get both quantitative and qualitative information about the atmosphere, the land, and the ocean from those bands. And the data are essential for weather forecasting in every modern forecast center across the globe. And indeed, in a framework of GEOS, satellites are exploited from a variety of applications: meteorological, climatological, ocean, ecology, as well as land. How did we get to this wonderful area that we are today? What was significant? And I tell you, in my thought, there were four essential components to getting where we got today: leadership, vision, understanding, and utilization. And as a young scientist, as many of you are young, there were people that I looked up to that helped lead us into this area. And I want to point out 4 people in the United States of America that were particularly important to us moving forward as a global community. There was David Johnson, the first true director of the National Environmental Satellite Service in the United States. And in fact, at the 25th anniversary of Weather Satellites, he was recognized for his leadership. This was a truly great man, and he helped establish monitoring of the globe from space as being a paradigm that will not change. I believe in large part because of his work we have the global observing system we do today of both geostationary and polar orbiting satellites. A man of extraordinary vision. Along with Dave Johnson was Vern Summy. And Vern Summy was a man of unparalleled vision. And in fact, his vision and innovation were such that we got the first Earth radiation budget experiment on a satellite, actually, but he's most well known for moving us to geostationary orbit, where we now observe all of the globe from 70 north to 70 south on a routine basis by countries across the world. This was the vision that Vern Summy had, observing from geostationary satellite. Then there was understanding. One of the brightest people I've ever associated with in my life, scientifically, was Dr. Tetsuya Fujita at the University of Chicago. And in fact, when I got my PhD, I requested he be on my committee because I wanted to make sure the absolute best in mesoscale meteorology and satellites was on that committee. He is recognized throughout the world in his leadership and understanding severe weather, tornadoes, hurricanes, and a variety of phenomena. And indeed, his 1951 publications on meso-highs, thunderstorms, and mesoscale analysis opened a new era of meteorology, mesoscale meteorology. He is the one who taught us how to do cloud motion vectors and pointed it out that in very small areas you can have large variations in the wind due to thunderstorm activity. His satellite and mesometeorology project papers were ones that we all cherished. And then there was Vince Oliver, who I worked directly for a number of years in the Office of Applications in NESDIS. He had a very thorough understanding of weather and clouds and weather phenomena and was dedicated to utilization of satellite data and would travel across the globe training people in that utilization. And in fact, after the first TIROS satellites images, they put together a photo mosaic where he actually analyzed the fronts, troughs, ridges, and airflow within that field. These people played a key role in getting us where we are in satellite meteorology today. Leadership, vision, understanding, utilization. Likewise, in China, you have similar people helping put together our global space-based observing system, which has grown very robust. And these people, a little hard to see in the picture, a little dark, but you all recognize, all have these characteristics of leadership, vision, understanding, and utilization, and indeed have helped move your space program forward and are helping move it into the future. You're indeed fortunate to have men of such wisdom, knowledge, leadership, and character, men and women, leading your space program forward. There are many components to a global observing system. You can recognize them here. Satellites are but one part of that system, but they are certainly a major component in that system. And we can look at various applications areas and requirements and system capabilities and see how different parts of the system can fit together for nowcasting or NWP or forecasting, what parts best fit together to give us the information. But we can't be content to stop with the system that we have today, because the needs of society, the needs of humanity are moving forward. Technology is moving forward, allowing us greater exploitation than ever before, and we must be able to take advantage of such systems. And indeed, this is part of the global Earth observing, or environmental observing system of systems. It has a number of societal benefit areas, and I think they believe they have invented something new here. However, we have dealt in this area for years. Weather and disasters, reducing loss of life and property from natural disasters, improving water resource management through better understanding of the water cycle. Certainly what we do deals directly with that water cycle. Climate change and variability, coastal and marine ecosystems, environmental factors affecting human health and well-being, dust transport, locusts, meningitis, weather and dengue fever with mosquitoes, improving the management of energy resources, water flow, rainfall, heavy rains, dams, how those operate, agriculture and desertification, and monitoring biodiversity. I challenge you to find one of these where satellites do not play a key role, and we have been playing them for years. As we take advantage of the marvelous growth that is going to occur in the future, there will be shifts in the way we do business. Change will become the natural way of doing things. The system will be a dynamic research component. That is, research satellites that are integrated with the operational system. They will not be a separate system anymore. We must plan for that not to occur. They have to be together. We'll have a dynamic data and product stream with a sophisticated user with a variety of needs. How we serve that sophisticated user to satisfy our needs will be a very real challenge. And merging of research and operations. That means a dynamic system and full exploitation. Products that are used or developed in a research mode will be used operationally in transition into operations. This type thing will often drive operational system managers totally crazy, because their operational system is continually changing its data stream. But to get full exploitation, this will be required. How we manage that balance between operational products and research products for operational exploitation. Continuous training will be required to do that. And you have a marvelous training facility here at CMATC. I have seen it. It is incredible. China is in the position, with your move to FY3, FY4, with your advanced NWP systems, your advanced ability to move data from one point to another, your advanced ability to communicate in ways with CMATC, to take a true leadership position in this global environmental monitoring and protection. And in fact, when I look at China being over 4,000 years old, with a culture that has gone back for many, many years, China must lead. You must lead. You have the background, you have the people, you have the sustainable knowledge. High priority areas. Let's get a little more technical here. GPS radio occultation for climate and high resolution soundings. Hyperspectral from geostationary is certainly going to occur. A global precipitation constellation with active radar. There will be hyperspectral in the visible to near IR. This may take a little longer and will likely be exploited in polar orbit first, but it will occur. And what will be very important will be formation flying with operational constellations of small satellites that work together with specialized satellites to measure such things as aerosol, winds, clouds, radiation, and so forth. But we're in a science of change. Think of the way things were 10 years ago versus today. Were you going to internet every day? Were you picking up your cell phone and talking to someone? Sending text messages? Life is changing. The way we communicate is changing. We are in a high-resolution digital age. We can launch into precision orbits. We're using research satellite data for operations. The distinction between what the sensors do at polar and geostationary altitude are shrinking. We have multi-platform, multi-sensor products that we put together today. And there's a change in the way we do business. Data handling, science and product development, training and utilization. For example, China is part of the virtual laboratory for education and training in satellite meteorology that is within CBS OPAG iOS. We're digital. Every spot you look at on the Earth has a continuous spectrum that can be used to analyze the Earth, surface, the environment, and the atmosphere. And that our surface can be either land or water. We're able to launch into precision orbits. In the past, when we would launch into orbits, they would drift very quickly. This is equator crossing time at 15-minute intervals for a polar orbiting system. And you can see that you'd launch into an orbit, and within 2 or 3 years, you had drifted over an hour away from time. So your climate record was much more difficult to construct. Your products were more difficult to put together and to maintain because of continuous changing solar viewing angles over time. So history was much more difficult to put together for exploitation. Now we can launch into very precision orbits where we only drift 15 minutes from the original launch time over a period of 4 to 5 years, greatly increasing the lifetime of the satellite. This ability to launch into precision orbits and actually with rockets control the drift of the orbital plane is allowing us to fly in formations with one satellite behind another by only a few seconds, taking near simultaneous specialized observations of the Earth. This is just an example of the launched and predicted drift of the NOAA satellites, some of them. And as I said, some satellites now are utilizing onboard fuel to help maintain more precise orbits and increase the longevity of that satellite. This is exceptionally important in a way. We'll get back to it in a minute. But I'll come back to this idea that when you can launch into precision orbits, your idea of what your satellite system looks like changes. Because you no longer need to launch huge satellites with 10, 12, 15 instruments. It may be a better architecture to launch 3 smaller satellites with instrumentation. Maybe they communicate back and forth to one another. I don't know exactly how it's done, but it's not hard in our computer and digital age with the bright people we have available. But these satellites operate, and then when you lose a component of that, you don't have to launch the entire expensive system, but can target and launch just a portion of that system to maintain your operational continuity. Research satellites are used routinely for operational purposes today. I point out that the ERS Ocean Wind satellite was used for a number of years. It's a research satellite. by operational centers. Today, radiances from AIRS data are used routinely as are quick-scat winds. MODIS data from Terra and Aqua are used to do a number of environmental applications, including fire monitoring. And indeed, China receives MODIS data directly and puts it on an advanced broadcast system for utilization throughout the country. We have multi-sensor, multi-platform products for things such as rain, using the TRIM satellite, rain gauges, and microwave instruments. We also take a number of pieces of information from different satellites to help us forecast things like typhoon and hurricane intensity. And that can be from rapid interval satellite imagery to see rotation within the eye, to the quick-scat winds, to ocean surface temperature and altimetry for heat content to drive this thermodynamic engine, upper-level winds from water vapor tracking to help see how the troughs and ridges interact with these systems to guide them, and indeed microwave data where we can make temperature anomalies to actually see the intensity of the warm core that drives the heat engine. There is just a marvelous amount of information, and that's just the surface. Changing the way we do business. NWP models of today want data in real time. With four-dimensional data assimilation or very stringent cutoffs for three-dimensional data assimilation in models, they want polar orbiting satellite data within 30 minutes of when that observation is taken. The Europeans put together the EATOVS system, European ATOVS Retransmission System. That system is now being linked on a worldwide basis with China and your Pacific partners here playing a major role in putting together a Pacific ATOVS retransmission system. The same thing is being done throughout South America. So within a few years, ATOVS data will be available to all operational NWP centers within 30 minutes of when those data are taken. Changing in the way we do business. We're not having to record it, store it, and send it back anymore. The mainstay orbits we still use, though, are the polar orbiting satellite orbit, sun-synchronous polar orbit, where we take observations from 2 to 4 to 6 polar satellites a day at the local sun time. We also have our geostationary orbits, where we are over the same part of the Earth, taking continuous imagery that allows us to make movies and track various features and evolve them. Watch them evolve. The thing I want to point out here is a few things that are fairly simple. Number one, from the low Earth orbiting satellite, we observe the effect of the process. With the geostationary, we actually observe the process as it is occurring and allow us to look at it in the future. And then there are other things that are the advantages of one system over the other. And it's foolish to get in an argument over which system, because the answer is both systems. Both systems have information to provide you on important meteorological features. Only a fool would say, do I keep the horse or the cart? They serve different purposes. You keep them both and they work together. We have prograde orbits when we don't want alias data, those such as measuring Earth radiation budget or rainfall. One such orbit is the TRIM. Another will be the Global Precipitation Mission. And we're moving into constellations and formations, where satellites fly in the same orbital plane, offset by just a few minutes. You can see here that the Aqua satellite is followed by CloudSat, then Calypso. Calypso only 15 seconds behind the CloudSat. Thank my goodness, that must mean one of them is on this side of the room and one is on the other side of the room. Won't they run together? Well, the answer is no, because at these polar orbits, satellites move about 3.18 or 3.8 miles per second. So they're separated by almost a half a mile or more. So there's a large separation, but they're very well controlled. And this is the future of where we're going in polar orbit, where you might have your operational FY satellite that the United States flies a CloudSat satellite behind in a research mode, and immediately behind that you have a hyperspectral satellite doing ocean research or detailed cloud information, where all are combined. But they don't have to have the AVHOR and other sensors on them, because that's on the primary operational satellite. But you use their information to help your products. This is where we must go. Another constellation that is very important, that is being demonstrated now, is the radio occultation measurements from satellite, where the low Earth orbiting satellite is seen to occlude as it goes, either it rises or sets through the Earth's atmosphere. There's a change in the travel time of the electromagnetic radiation, and you get a very good idea of temperature across about a 200-kilometer baseline. That's a long baseline. However, with advanced NWP models and four-dimensional data assimilation and tomography used in that your scientists must be working on, I am sure, you will be able to come and make very high-resolution vertical soundings that are higher resolution than the 200-kilometer baseline by using the power of other observations in the numerical weather prediction models assimilation system. So you have the satellite data, the assimilation system, and the model. And this assimilation system that is put together is the synergizing mechanism to bring together a number of these observations and make them into finer resolution and put them some into NWP, some as a sounding into a forecast office, some going off into a climate record. Multiple uses out of that system. Over the next 10 years, we'll gain a lot of experience with these type of instruments, the hyperspectral, multispectral, passive and active microwave sensors, LIDARs, GPS. Some of this will become operational, some will remain in a research mode, but we must blend them together effectively. When we look at things, we have to realize the spatial and temporal domains of what you are observing dictate what the satellite systems, and I mean systems. You see, in the U.S. it's very important where you put this little apostrophe. If I put it here, it's just a single system. When I put it out here, it is the larger system, a system of systems. What those spectral needs as a function of space, time, and signal and noise are. And we must have spectral awareness in that area. I will go through some science things very quickly now. We've been going through them in the classes that I am teaching, but to give you an idea of what do we mean we observe at different resolutions and times and so forth. Well, temporal is the easiest to understand. This is a hurricane eye at 30-minute interval, 15-minute interval, 5-minute interval, and 1-minute interval. And for this particularly strong hurricane, it wasn't until we got to 1-minute interval that we clearly saw the cyclonic rotation within that eye wall region. And there are a number of reasons you might wish to look at this in 1 minute as a hurricane approaches coast. There are vortices that will develop unstably around that eye wall, but when they develop, they spin up very rapidly and then decay into turbulence, but they are extremely destructive regions. If you're looking at agriculture, you don't need to look every minute. If you looked at agriculture grow every minute, you'd probably go mad or either be a poet by the time you were done. You look at a time scale appropriate to the growth of agriculture. And then you turn and you see where it's being unhealthy growth, less green, or where more green appears at different times of the year. And you go back and you compare these with La Nina and El Nino, or other seasonal oscillations, and then begin making long-range predictions. of vegetation health, heavy rainfall, and other things by using the appropriate observing time frequency and your constellation of information. You can look at spatial resolution. Here you might be looking at a hurricane eye at 1 kilometer. You come with a polar orbiting system and you get 250 meters. Much more detail. You must learn how to use them together, because here is one of these small vortices along that hurricane eye wall that can be so destructive. What wavelengths do you use and how wide those wavelengths are? We taught one whole day of this last week on spectral bands, their applications, and the use of a tool named Hydra to do analysis of the spectrum. I will not try to cover that here, obviously, but I will show you something very interesting. This is going from the visible to the near-infrared portion of the spectrum, or from about 500 nanometers out to 2500 nanometers, or 0.5 to 2.5 microns. Your eye looks in this region. When we're in this region, small particles such as smoke and haze and dust scatter very effectively. In fact, there's me scattering down in here in the blue portion of the spectrum that scatters and gives you the blue sky that you look at. As you move to longer wavelengths, you'll notice the smoke goes away. I'll do that first. So if we choose the right portions of the spectrum, we can see smoke, dust, haze. But when we do, we must compare that with another portion of the spectrum where the wavelength is longer and you don't see the dust, smoke, or haze. There are also changes in Earth's surface characteristics. While we think of this as a reflective portion of the spectrum, which indeed it is, there is also emission when you get large fires. And this is actually emission from a large fire over this region. So again, being spectrally selective in what you look at, whether you're deep in a water vapor absorption region or whether you avoid that region, can give you different information on this scene. And in fact, when you go and do analysis at different pixels, you remember I said every pixel had digital information about the Earth, its environment, across the spectrum. You see there's a very real difference between the way the cloud's brightness appears versus that of the fire, which begins to show up distinctly at longer wavelengths, versus water, which we think of as being dark past 700 nanometers, but it gets bright again out past 2 microns. Grass, bare soil, all of these things take on different characteristics. So in the idea of a GEOS framework, we can actually go in and digitally take apart an image and talk about agriculture. We can talk about pollution. We can talk about the environment. We can talk about the thermal field and its importance. This is, for example, a image at 6.7 microns going broadly across a spectrum with lots of absorption and emission throughout that spectrum. And we utilize that information to do things like temperature sounding of the atmosphere. We need to be aware spectrally of whether clouds are bright or not bright, depending on what part of the spectrum we're in. We need to understand things about the Earth's surface characteristics, because it will appear different over a desert than it will over a vegetated area. I'll give you examples of some of this now. This is a movie of visible satellite data. Here we have ship trails. Those ship trails we'll also see right here as very bright. But you'll notice this bright cloud up here in the visible data is black when we're at 3.9 microns. This is because it's very thin cirrus. You'll notice streaky little clouds over here. These are jet contrails with very small particles that we're seeing in that area. We see bright cloud over here, and we see this cloud moving down, which is actually dark. I'll animate this for you, and now you can see very clearly the dark cloudiness moving down on the right-hand side of the picture over here. The dark cloud moving down. It's bright in the visible. Dark up here in the 3.9 micron channel, but bright in the visible. Ship trails showing up very, very well. And if you can see out in this area beneath the hand, and I doubt you see very clearly, but these will be left with you for future use, there are a lot of bright spots out here which are actually fires showing up in the 3.9 micron channel. So we're able to do a number of things with that channel. The area turning black down here, where I put the little hand, is not cirrus cloud. That's where the detector has saturated because we didn't have enough bit depth to look at the hot area. And this is an important consideration as you move forward with your 3.9 micron channel considerations. During the next decade, we'll get experience with all of these satellite data again. We have a robust constellation now of geostationary satellites. You can see the ones over the area where you look. We have very nice polar orbiting system right now that's being improved. The ones in red on the bottom right are more land observing satellites, whereas in the black, the top, are weather, and then we have rainfall, winds, altimetry, and GPS. That all fly underneath this beautiful geostationary system. What do we look like in the future? It will be a much improved system for operations. A number of beautiful observations over the Pacific Ocean region and Indian Ocean region from geostationary altitude. We'll move into advanced imagers on all of these satellites. From polar orbit, we'll have a very rich system with the FY3 system in the morning and afternoon orbit. We'll have a very early in the morning INPOS orbit and an afternoon orbit with METOP in the AM. How these systems are put together in synergy is a very important consideration as we move forward. Do we fly in the same orbital planes close to one another? Do we offset by 30 minutes? Do we change our altitudes by a few hundreds of kilometers so that one satellite's plane appears to drift under the other one and you get coincident observations in off time? All of these important considerations need to be taken into account as we plan our system so that we get maximum benefit for all mankind. There are a variety of spectral regions that we're looking in. We need to coordinate spectrally where we look in this rich spectral environment in which we live. Some channels are good for one thing and not another, and how we utilize the different channels and blend them together and get the different information that we do from this conglomeration of information is very important. That's for the vis to near IR, that previous slide. That's visible to near infrared. You can see the wavelength on the bottom. And here the wavelength is in microns, and this is for the infrared portion of the spectrum. Again, you can notice we're imaging almost the entire emitted portion of the spectrum. And we observe those parts for very, very good reasons. And that's part of the courses we've been teaching. But how we do this is a system in synergy with other people so that we can blend data together from MTSAT, from FY4, from Meteosat, so that we get a continuous water vapor channel, for example. The modeling, how we do that becomes important. There are a number of channels for ocean color, just to show that. So high payoff, high priority. Hyperspectral from geostationary and from the visible to near infrared. We see the U.S. missions leading to the future GOS, and the advanced concepts that we're looking at include hyperspectral, imaging lidars, CO2 lidars, synthetic aperture radar. And we'll end up getting a number of different channels, and that's what each one of these little boxes are, looking spectrally. And we can put those channels together to make a color combination to try to emphasize some portion of the spectrum. We can spectrally separate brightness values in one channel versus another and do cloud or land or ecological type identification. I don't expect you to try to understand these. It's just to show you that when you look spectrally, you see different things, as we saw, and how you put that together is important. We can also take the multiple channel data that we have and do different types of analyses, such as principal components, which is very much like a Fourier series with the different amplitudes representing different pieces of information. And you put those back together then, recombine those Fourier series type of images, or principal component images, you might like to call them. And then through study, you might be able to find things like dry lines, thunderstorms, cirrus cloud, low-level moisture, middle-level moisture. And instead of presenting a user with 50 images, you present them with one image that contains all of that information because of the advanced mathematical analysis that you do of the imagery to then put together into a product. Another high payoff, GPS, when it's put in synergy with the polar orbiting system, with the hyperspectral sounder. Now this is something that should come out of your analysis system. And it would be a place where you go in and you do a radio occultation tomography across this area, and that's in your system. Then you have the hyperspectral soundings all throughout this system, and by combining them together, you can get temperature profiles, as we've done in simulation, whose accuracy is better throughout the troposphere than 1/2 degree Kelvin. 1/2 degree Kelvin, and about 1 kilometer or less in the vertical. That's incredible. Moisture within about 10 to 15% throughout the troposphere, which says maybe there are other areas we need to begin looking for this very, very low boundary layer moisture in our synergy system. But either one of these does not give you the performance that the synergy from that system does. So again, GPS and hyperspectral. European missions leading to the advanced GOS, we're most excited about the wind LIDAR system that will give us winds for the first time from a polar orbiting satellite, and then the ocean and ocean salinity, as well as soil moisture from L-band microwave. These are very, very exciting on the future. This is a hyperspectral infrared image of a dust storm. And I'll just point out, by understanding the spectrum, you can see the dust. You can also see differences in vegetation and soil type by using your infrared channels. Why is this important? Well, in this part of the world, and I'm sure partly out of the Gobi, with the dust front comes meningitis, comes various vector-borne diseases that are transported through this dust front. Also, locusts come with that because they fly and then will land and devastate crops. So again, health, ecology, things that you may not immediately think of, you can see very beautifully when you use multi-channel satellite imagery. This is just that same dust region in the visible portion of the spectrum. This is the atmospheric dynamic LIDAR mission that we're so excited about for aerosols as well as winds. Japanese missions to the future of the Gauss, looking at hyperspectral. They're a key player in the global precipitation mission, but the hyperspectral I'm most excited about is on what's called GOSAT, that's greenhouse gases satellite. The GOSAT is hyperspectral. It's fairly low resolution imagery, 8-kilometer fields of view, but it will look in detail in the visible to near IR portion of the spectrum, in the oxygen A band hyperspectrally, out here in this CO2, H2O, and methane region, and it will also be hyperspectral across the infrared portion of the spectrum. Russian Federation is going to continue their active radar activity for looking at ice, and we look forward to continuing to get information from that. India will have their IRS follow-ons as well as continuation of the INSAT program. The IRS P4 will have an ocean color mission as a part of it. For example, medium resolution microwave system on that. And those data can be used for a number of applications. Chinese missions to the future of the Gauss, looking at hyperspectral from various orbits, geostationary microwave, conical microwave, as well as new initiatives that might even include geostationary microwave. So advanced systems coming up from the Chinese, who already have a variety of products. You know them since you're the Chinese people, but those products continue to grow and be more and more robust and more able to be used. There are orbital issues that need to be addressed. There will be a convergence of orbits near the pole, providing a wealth of information north of 70 degrees from a synergistic polar system. You can actually make movies over the poles if we learn how to share all data and put them together from different countries. Constellations, again, I've talked about this, is the wave of the future. You can actually take constellation data where you have 3 satellites being 30 minutes apart in polar orbit, make images from those, and make movie loops, just like you do from the geostationary system. So you can imagine movies up over the polar regions in daytime from your polar system at high resolution. Formation flight. Things like CloudSat, where you put together research objectives along with an operational system. So high priority, formation flying, aerosol winds, cloud LIDAR. A few examples of synergy, intercalibration. If we have a highly calibrated geostationary system, all polar orbiting satellites will fly under that, and we can do intercalibration. So spectrally, we can calibrate our entire space-based observing system, meaning we have no questions anymore about climate from satellites. Radio occultation, first order measurement. Synergy to look at ocean phenomena, altimetry for depth, water temperature, as well as currents, where we can actually see the return of the current with La Nina. NWP, it's a global observing system to do NWP. Even one day NWP, you've got to have observations away from the global system. And you say, why? The sphere of influence is only very small. That's not true because modern NWP analysis systems have background fields, and those background fields develop over a week or longer and are critical to the information that you put in to do that 1 or 2 day forecast. So you have to have a global analysis system that is high quality. I'm sure you've seen this before, but in a period of decreasing Raywin-sons, there's been a magnificent increase in performance in both the northern and southern hemispheres in NWP capability. That is due to satellite data. Very clearly. Very clearly. High temporal and spatial resolution from geostationary become important, especially when we can put those together in an adaptive observing mode with high resolution soundings for severe weather applications. Finding inversions. So the phenomena being analyzed helps define the system that we use, and we must be very brilliant on how we go about deciding how we will put that system together. So as we take advantage of the future, paradigm shifts will be required with the system, with data, products, and dissemination, and how we merge research and operations. There are high priority areas that I've already pointed out to you that we must look at as we go to this system. There's a vision for the global observing system at 2015 that is being revisited now after just 5 years because it has become so much more energetic. But what's significant as we move to the future? And the data and systems are certainly significant, but the most significant thing as we move to the future is going to be leadership, vision, understanding, and utilization. Those are the 4 cornerstones upon which you will build. And without that, one of these is weak, all are weak. The advancements we're seeing are natural and are going to provide exciting opportunities with truly adaptive observing systems in the context of a global Earth observing system of systems. Thank you.